Hello everyone, welcome back to our generator protection playlist. In this video we will exploring the overexcitation and the 24 volt per hertz or V over F protection, commonly known as 24 in the ANSI code of protection. So this function protects the generator from excessive V over F ratios, which can cause magnetic saturation, overheating and insulation damage. We will discuss how overexcitation occurs, its typical causes, and how modern relays calculate the V over F ratio to provide both warning and fast trip protection. Additionally, we will go through a step-by-step testing procedures, including how to verify the backup and the trip characteristic of both the warning and fast trip stages using the Test Universe modules. And by the end of this video, you will understand how overexcitation protection keeps generator safe under abnormal operating conditions. So here we can look at the overexcitation protection, which commonly referred to be a 24 protection. So as we explained, the modern excitation systems often include overexcitation limiting and protection, but it may take several seconds for the system to respond. So the overexcitation occurs when the V over F ratios exceed about 105% at full load and or 110% at no load. So typically V over F relays are set around 110% with a time delay of 5 to 10 seconds to allow for normal transient. It's important to note that the generator overvoltage can occur even without exceeding the V over F relay setting, for example, during the large overspeed conditions in hydro generators. So this protection ensures the generator and associated equipment are protected against insulation stress and potential damage. Now, the overexcitation or the V over F causes or problems can be caused by a variety of factors, including the generator voltage regulator issues, the operating errors during offline manual regulator operation, control failures, or failures in the voltage sensing circuit, such as a VT fuse loss. So, a system level events like sudden unit load rejection or power system islanding during the major disturbances can also lead to overexcitation. So, the 24 protection function ensures that generators and transformers are operated within their rated kilovolt ampere or megavolt ampere voltage and frequency limits. So the overexcitation occurs when the voltage to frequency ratio exceeds the design limits, saturating the magnetic core and inducing stray flux into non-laminated components. This leakage field, which increases with the voltage and decreases with frequency, can lead to higher losses, overheating, and eddy currents, causing interlaminar voltage that degrade the insulation. So equipment damage is mainly due to the component overheating, which is a timely dependent process, highlighting why overexcitation protection is essential. So as you can see from our figures, here is the actual generator overexcitation event occurs when the V over F ratio exceeds the generator design limits, typically due to a combination of high voltage and low frequency conditions. So the overexcitation protection is used to protect the generator against excessive V over F, also called overfluxing. So in legacy protection schemes, this was typically implemented using a stair-step approach with two definite time set points. One of this element might be used for triggering an alarm, while the other provides a fast trip for high overflux condition. However, such schemes often either overprotect or underprotect the machine. So the instantaneous reset features also ensure that the relay returns immediately once the condition normalizes. Flux density also is a very effective indicator of no-load heating, and manufacturers usually provide the curve showing the permissible V over F operating limits for their components, often in inverse time characteristic format. So this curve guides the setting of the overexcitation protection to ensure safe and reliable operation. In modern overexcitation protection, the relay uses both definite time element and inverse time curve, allowing for better coordination with the generator manufacturer recommendation. The inverse curve are selected to match the machine thermal and magnetic limits, providing more precise protection compared to legacy stair-step schemes. Modern relays also employ a settable integrating reset, which gives the relay a kind of thermal memory to account for repeated overexcitation events. This ensures that the generator is protected from cumulative thermal stresses. Typically, the manufacturer provides the V over F curves showing the permissible operation limits which guides the settings. So many modern relay combine definite and inverse time characteristics in a single device, optimizing both fast tripping for extreme events and thermal-based protection for repeated and less severe events. As you can see from the curve here, here is the V over F, as you can see, and we have both stage. One of them is inverse time V over F, and the other one is a definite time characteristic. So the 24 overexcitation or V over F protection calculates the ratio of the applied voltage to the applied frequency and compares it to the generator nominal induction, often represented as P or Pn, which is the nominal inductance. So as you can see, here is a setting of Siemens relay 7UM62. So you can see here the overexcitation function is on. The V over F pickup is 1.03 in per unit values, and the time delay is 10 seconds. The second stage, which is V over F double greater, picked up at 1.4 per unit, and the time delay is equal to 1 second. And here is the characteristic tab, which simulates the time characteristic of trip time delay based on the V over F values. And here is the equation. You can see here the applied voltage and the nominal voltage setting, applied frequency and the nominal frequency. So if the calculated V over F ratio exceeds the configured limit, the relay initiates a time delay trip to protect the stator core from thermal stress and potential insulation damage. So this approach ensures that the generator is protected against overexcitation while allowing for a short-term acceptable transients without unnecessary tripping. Okay, so the V over F always in per unit values. The overexcitation protection function continuously calculates the V over F and compares it to the generator nominal induction. So if the measured V over F exceeds the configured limits, they initiate a time delayed trip to protect the stator core from the thermal image, and this trip time is determined based on the selected curve and the degree of overexcitation, often expressed in per unit values, as we explained. So you can see here the overexcitation protection parameter setting. So V over F greater is 1.03, and the time delay is 1000 seconds. So here is part number 2 on the curve representing the thermal tripping with different ratios and different time delay based on the value. So here is the V over F on the horizontal axis. Here is the trip time delay in the vertical axis, and you can see here the trip time characteristic for the overexcitation protection. And part 3 representing the second stage, which is the V over F double greater equal to 1.4 per unit with a time delay equal to 1 second. And here is the tripping criteria as we explained. So when testing or setting the overexcitation protection on the relay like the 7UM62, it's important to distinguish this function from the voltage protection, over voltage and under frequency protection function, because this protection can overlap, and also to determine the maximum permissible test voltage and test current, which is critical to avoid unintended operation of other functions during the test. So for this reason, it's important to determine the maximum permissible values for the test voltage and the test frequency, and this calculation can be done as you can see on our screen. So the V maximum can be 60.622 multiplied by 1.03, which is setting, and 60.622 because it's 105 voltage divided by root mean square of 3. So you can see here is a V over F 1.03 volt per hertz, and also for the transducer, which equal to 100 volt, and here is the 57.735, which is line to neutral value, and the V over F double greater equal to 1.4 volt, and here also the nominal frequency 50 hertz, and the trip time of the double greater stage, which is equal to 1 second. So the over voltage parameter functions of the over voltage protection is set to 120.80 if you remember from last video, and in the line to neutral, which equal to 69.744, and the under frequency equal to 47 hertz. So we have to calculate the V maximum and the frequency minimum at both cases to avoid any interference of the over voltage or under frequency protection function. So the V maximum can be calculated using the formula 60.622 multiplied by 1.03, so which equal to 62.44 voltage in the line to neutral value, and the frequency minimum also at 100 voltage we can calculate it also from the formula, so it will equal to 46.231 hertz. So using these values to ensure that the testing focuses on the overexcitation function without triggering the voltage or frequency protection unnecessarily. Now we will talk about testing the warning stage or the V over F greater pickup value of the overexcitation rotation. So the test universe ramping module is used to verify the relay response at the defined V over F limits. So for proper testing, the local hardware configuration must be set correctly as we explained. So 3 voltage output should be mapped as a phase to neutral voltages, and the start signal must be connected to a binary input. Since the V over F ratio is only relevant parameter for this test, so both the test voltage and test frequency signals can be varied simultaneously. So as you can see from our screen, this approach ensures the overexcitation function is tested without triggering the voltage or the overvoltage or under frequency protection function. So in the detailed view also, if you can see in the detailed view of the ramping module, so the reset thermal replica signal can be used to automatically clear the thermal memory of the overexcitation protection for ramp 1 and ensuring accurate measurement of the relay response. So you can see here the test module setting, which is a test view of the ramping module. So we have 3 ramps: ramp number 1, ramp number 2, and ramp number 3. So ramp number 1, here is the we will control the voltage, 3-phase voltage, as you can see the magnitude of them, and the signal 2 also we can control the frequency of this voltages. So we can make it simultaneously a V over F ramping up of the voltage and ramping down of the current, as you can see, to get the V over F parameter setting values. So you can see here the assessment also of this ramp view. So for ramp 2, for example, the voltage will be ramped up from 60.6 to up to 69.74 with 100 millivolt step size, as you can see. And on the other hand, which is the signal number 2, so the frequency will be ramped down from 50 hertz up to 49.8 hertz. So now you can see the stop condition in ramp 2, the start contact will change from 0 to 1. On the other side, on ramp 3, as you can see, we will make ramp down for the voltage value from 69.74 volt up to 60.62 volt, and we will make ramp up to get the drop off value of the V over F ratio. So ramp 2 for getting the pickup value, and ramp 3 for getting the drop off value. And you can see here the ramp 2 is used for in the assessment view to check the pickup voltage and the pickup frequency, and the ramp 3 is used for assessment of drop off voltage and drop off frequency. And you can see here the arithmetical verification of the measurement results. So for example, if you take this result, so the V over Vn generator 62.42, which is the actual value, divided by the nominal one, which is 60.62 volt, and the frequency, which is 49.961, which is divided by the nominal frequency, which is 50 hertz. So you can find out that the ratio is 1.03, which is stage 1 of the overexcitation protection function. Okay, now we will talk about testing the tripping characteristic of the overexcitation protection. So the trip command here must be mapped to a binary input, not the start contact. So it's important also to note that the testable portion of the V over F tripping characteristic is limited by the potential overlap, as you can see. So it might be have overlap with the frequency protection or the overvoltage protection function. So for this reason, only some test points can be defined in practice. For example, we are defining 1.2 here in V over F in per unit value. So using the statistic concept estimate, the tip time can be measured for a selected test point. Also, the healthy state, which is the state number 1, as you can see, with nominal frequency and nominal voltage for about 3 seconds, can be also used for ensuring the test start from a well-defined nominal operating states. Also, before performing this test, the relay thermal memory should be reset to ensure accurate assessment of the tripping characteristic. So you can see here from the state sequencer test view. So state number 1 would be healthy with nominal frequency, nominal voltage for about 3 seconds, and state 2 will be represented by V over F, which equal to 1.2, as you can see, for 1.5 multiplied by the expected trip time, which is equal to 90 seconds. And you can see from here for the trip time characteristic, as you can see, so at 1.2, which is our preset value here, so you can see the expected trip time to be 60 seconds. That's why we can put the state number 2 to be 90 seconds, which is long enough to take the assessment of the protection relay. State number 3 will be off to reset the relay, and here is the time assessment, which is starting with state number 2 V over F at 1.2 per unit, and the stop will be with the off or with the trip contact, which expected to be 60 seconds. Okay, now we will talk about the fast trip stage or stage 2 of the overexcitation protection function. Also, the testable part of the V over F tripping characteristic is again limited by the potential overlap with the frequency and the overvoltage protection function. So in this example, we will use one test point also are defined and used for this trip time characteristic, and using the previously mentioned calculation, the corresponding voltage and frequency setting can be calculated. For instance, the V over F ratio of 1.3 in this case. So you can see also, as you can see here, actual ratio is 1.3, as you can see from the test view of the statistical answer. So state number 1 again is a healthy for 3 seconds. State number 2 is a V over F for 1.3 per unit value, and also the expected trip time to be 1.5, the expected trip time. And you can see here the expected trip time of 1.3 is equal to 19 seconds. So 1.5 multiplied by 19, it will be about 28.5 seconds. So you can get the trip time of at V over F equal to 1.3. So you can test also the curve in between, which is represented by number 2. So we are tested the value at 1.2 and also at 1.3. Now we will talk about the highest stage, which is the double greater stage of the overexcitation function, how to test it, which is more challenging due to the potential overlap with the under frequency and the overvoltage protection function. So the backup test for this stage is only possible under a certain condition. So one approach is to use the ramping test module while externally blocking the under frequency function, for example, using the circuit breaker trip signal or open signal. So since the V over F ratio is the primary parameter of this test, the voltage is set to its maximum and only the frequency is varied. So for example, if the overvoltage stage number 1 V equals greater is 120.8 volts, then the phase voltage used would be divided by root mean square of 3, which is about 69.74 voltage. Also, if external blocking is not possible, the V over F double greater stage must be configured as a separate signal to allow the testing. Additionally, also to prevent the interference from the thermal tripping characteristic, the thermal memory can be reset permanently for all ramps in the detailed view, ensuring accurate assessment of the instantaneous trip response. So you can see here the ramping test view. Here is the setting. So ramp 1, we doesn't need any binary trigger. We will inject the nominal voltage with the nominal frequency, and in ramp 2, we will expecting a tripping from 0 to 1 to trigger the ramp 2, and the nominal value will be 66.26, and the nominal frequency will be 39.037 as we explained. So you can see here also the signal number 1 to be the frequency, as you can see, and we will fix the voltage in this case. So we will ramp down the frequency until get the trip so you can see here the backup value of the ramp 2 with the trigger condition of the trip contact from 0 to 1. You can see the nominal is 39.037 hertz and the actual is 39.494 hertz, but still assessed as passed because it's in the acceptable limits deviations here. So you can see also the test limits for the maximum permissible test voltage as we explained before. So the Vtest equal to 95% of the phase to earth voltage, which equal to 66.26, which is the value here, which is fixed in the analog output of the ramp 2. You can fix the Vtest to be 66.26. Also the nominal frequency at this ratio, which is equal to 1.4. Also you can expect from this ratio what is the value of the frequency. So for example, 1.4 equal to V over the nominal voltage, all of them over frequency over the nominal frequency. So we know this value now, which is 66.26 volt. The nominal voltage of the generator is 60.62, and the frequency which is need to be calculated, and the nominal frequency which for sure is 50 hertz. So you can calculate the expected frequency, which is 39.037 hertz. So here is the expected value or the nominal value, and we can measure this backup value of the frequency. So now we can make the backup value of the V over F double greater. Now we will talk about the tripping characteristic also for the second stage of the V over F double greater. So as you can see, we can use the statistical answer again for testing the tripping characteristic of stage 2 of overexcitation protection, which requires also a special consideration due to the overlap with the under frequency or the overvoltage protection function. So this test is only possible if the trip times of the under frequency protection are longer than the V over F double greater stage trip time, or if the under frequency and overvoltage protection functions can be externally plugged. Alternatively, the V over F double glitter stage must be configured with a separate trip command to allow the independent testing. So these precautions ensure that the V over F double glitter stage can be accurately evaluated without interference from other protection function. So you can see from here now state number 1, state number 2 at 1.5 per unit value of the V over F, and state number 3 which is off. So you can check the trip command, or you can use the trip command as a trigger condition for the state number 2 to test the trip time of the second stage. And if you see at this value depends on the trip time characteristic on the right hand screen here at 1.5, so the trip time will be 1 second, as you can see. So after 1.4 the trip time always will be 1 second. So we can inject the state number 2 for 2 seconds, but we are expecting nominal time for 1 second. So thank you. Here is the end of our video, and stay tuned for the next one.